Okay, this morning, everybody, we are starting some water properties and buoyancy. I just don't have the correct ILM, but I have this one. So we're going to start through that one. And today I will highlight what we're going to talk about. So today we're going to describe chemical properties of water and effects of temperature. We're going to state the 3 laws of buoyancy and the effects of buoyancy on regular shaped objects submersed in water. And that's about it. These other things, they actually put these 2 things in heating. And Marty should be talking to you about heating, about flow of water, Venturi, cavitation, simple head pressure calculations we already have done. And then the gas laws come in 3rd year gas now. Okay, I'll maybe just touch on those later. So we're going to do the first 2 objectives here, and that should cover the entire ILM, I believe. All right. So let's go down. When we start talking about water and properties of water. Oh, why is this in the way? There, get out of the way. There you go. Now, when we start talking about water, and when we have effect of temperature in hot water heating systems, and I'm also going to say in domestic water, because something happens when water is heated for domestic applications as well. So water is a chemical compound. It's H2O. We know that, right? There is a water molecule right there. H2O is the most abundant compound on Earth. It is the most abundant compound on Earth, and that's why we talk about Brett 070206D is the ILM. Now, although water is very simple atomic composition, it does possess some unique characteristics, as we already know. Now,
I'm going to draw another right-angled triangle because we have to solve for this piece right here. This piece right here is my travel, and here is my right-angled triangle on that.
Okay, so we are back here. Now, what happens with water is it produces a very strong bond between the hydrogen and oxygen. So if hydrogen was floating around out in the atmosphere and we have the oxygen molecules floating around in the atmosphere, what happens is that they attract very quickly to each other. It's something that they do. There's a very strong bond because of these positive and negative charges. Okay, and you get this strong bond happening. That's why it is the most abundant compound on Earth. And when I say compound, it's where 2 elements like hydrogen and oxygen, when it comes together, it becomes a compound. These are single elements, each one on its own, and they just like to attach to each other.
Are you sharing your screen right now with us, Doug?
I thought I was. How about that?
That's better.
Okay, sure. There you go. So this molecular bonding down here talks about the strong surface tension and cohesive forces exhibited by water. Now, do we know what strong surface tension means? You ever see out in the swamps, whatever, you have the water there, and then you have these little bugs with their little legs and they stand right on top of the water. That is a strong surface tension for that water. It's like when my wife makes gravy, you know, and you have that skin on top of the gravy after a while. That is a strong surface tension. Again, water is known as the universal solvent, and it's capable of dissolving numerous compounds. And we use water all the time to do that.
So surface tension would also be like the water on top of a glass when you get it like real full, but it's not spilling over kind of thing, or is
That's
that?
right. That's exactly.
Oh, okay. Good.
Yeah. Now, there is some different things that we have to know. So chemical properties of water, and when we talk about pH, it is the number of hydrogen ions. That's what pH means. It's presence of hydrogen ions. Okay, this is exactly what it means. And hydrogen ions are water molecules consisting of 2 atoms of hydrogen and 1 of oxygen. See, just like that, H2O. And the energy is nicely balanced. Now, the pH of water, or the presence of these hydrogen ions, can be broken down into 2 parts. One is hydrogen ions, and they are positive, and the other is hydroxyl ions, and they are negative. Now, here's the thing. When you do water softening, etc., this is what they're trying to take away. They're trying to take these hydrogen and hydroxyl ions out of the water so it is more neutral, right? So if you have more hydrogen ions, it becomes more acidic, or again, more hydrogen ions, it becomes more acidic, okay? And then the less, it becomes less acidic. So we'll talk about that in a second. So these ions, they start talking about atoms, and they're made up of 3 components: a nucleus, neutrons, and protons. And these electrons circling the nucleus, you see how the electrons are circling this nucleus here, where the protons and neutrons are. So these changes or charges cancel each other out and result in a neutral atom. But when energy such as heat is added, it moves to a higher energy level. So these start to move farther outwards. These electrons move farther outwards is what happens when it's heated. So something happens to the water when we heat it. So if energy is high enough or warm enough, the electron will leave its atom and become a free electron. And when the atom loses an electron, the atom will be left with a positive charge, or known as a positive ion. So similarly, an atom may pick up that free electron and then it becomes negative. So it's just whether it gains or loses electrons, whether it becomes positive or negative. Okay. A hydrogen ion is really a hydrogen atom with a positive charge that requires 1 electron to balance it. So similarly, hydroxyl ion is an additional electron that gives the hydroxyl ion its negative charge. And remember, electrons are always negative, right in there. So in neutral water, neutral is what we're trying to say, neutral, and I'm going to give neutral a number 7. So neutral water is a pH of 7 is neutral. And this is where the number of hydrogen ions and hydroxyl ions are exactly equal, okay, in a concentration of, and they give you how many grams per liter. That right now is not really important. But what is important, if the hydrogen ions, the positive ones, increase, the hydroxyl ions must decrease because the total quantity never changes. Also, when this happens, the acidity increases. So in the presence of hydrogen ions, you get higher acidity. Okay. And then they go on to talk about muriatic acid. All right. So if the quantity of hydrogen ions decrease, then the quantity of hydroxyl ions must increase. And if these increase, it becomes an alkaline, or sometimes known as a base, right? Okay.
So Doug,
Yes, sir.
so hydroxyl ions will make it basic. Hydrogen ions will make it acidic.
Correct. Very good.
Thank you.
Okay, now we have to look at the pH scale. And here we have a pH scale here. And as I said before, number 7 right here is considered neutral. Okay. Now, anytime we times, each level here is a times by 10. So there is 10 more, times 10 more hydrogen ions. 10 times more hydrogen ions, 10 times more. So as we go times 10 higher, we get more acid. And if we go the other way, less hydrogen ions or hydroxyl ions, you become highly alkaline or a base. So this is an acid, and this is a base. And this is the pH value in which we do this. So more hydrogen ions, more acidic, the number goes down. Less or more hydroxyl ions, the number goes up. And it's a factor of 10 it's based upon. Okay. And then I'm going to go over to the list and we're going to talk about things that are acidic. Okay, I'm not going to read all of those things, all that stuff on there, but I do want to talk about acidity. So neutral right here, as you can see, distilled water, perfect, right? Rainwater is actually slightly acidic. Now, when a lot of pollution is put into the atmosphere will pick it up and then put it back through the water vapor that is in the clouds, etc. And if you have a lot of H2S gas up in the atmosphere, you're going to have acid rain, which is not good, right? And the burning of coal, and it's still clean fired coal is different, but in the olden days when they burned just coal for energy, it produced acid rain. And it was a big problem in Ontario and Quebec. It was killing off forests, etc. So look, boric acid is just slightly acidic. Orange juice, look at this. Orange juice is moderately acidic. Vinegar, strongly acidic. Lemon juice, extremely acidic. So listen, if you have problems with acid reflux, lemon juice is not your friend. It's just going to create more acid in your stomach. Very extremely acidic would be your stomach. It's terrible, right? And look at this orange juice. And you know what this affects also? Your teeth. So if you like to drink a lot of juice, etc., you know what? Use the straw that the little box comes with because you want to protect your teeth. And then less hydrogen ions or more hydroxyl ions, you get a base. And baking soda is a strong alkaline, beach ammonia, drain cleaner, except we could also in here put soap. as very much a base, right? Anything that's slippery is considered a base. So if it's slippery to the touch, it's more of a base. If it's gritty, it's more of an acid. So you can tell by that as well. Now we want to talk a little bit about water hardness. Water hardness is caused by the presence of dissolved minerals. In southern Alberta, we have very, very hard water. Does anybody know why?
Calcium?
Well, we use glacial water, and all of our water runs on those rocks and picks up all the minerals out of the rocks, and we treat it and then we drink it. So it's got a very high mineral content in it. It just picks up all of those ions, etc., and that's what it does. But this hard water that has a lot of minerals in it tends to reduce the cleaning ability of soap and detergents. Does anybody here have a water softener? Anybody in the room? Just shout out if you do. Nobody? Oh, Dawson?
Yeah, I do.
Yeah. Well, you could probably get a good soapy lather going in the shower, can't you? But it leaves a little bit of a film on your body, a little bit of a slimy kind of feel. And that's how that is. But you don't want to drink softened water. So if you guys are ever putting these fixtures in or water softeners in, remember, drinking water should not be soft. So do not soften your drinking water. So you will have to plan out how you're going to install these water softeners compared to the rest of the house. You don't want to put softened water on your lawn, for example. You don't want to put softened water in your toilets. Why are you going to treat this water and then just flush it? Okay, that kind of stuff. An easy and quick way to do a lot of this is just soften the hot water going into the tank. That is one of the quick and easy ways without compromising the rest of the system, especially if you're doing an install after the house is built. Now, water treatment is humongous business. All right. If you want to get into a niche kind of business as a plumber, water treatment in southern Alberta is an incredible amount of business. Okay, so right here, I don't want to overlook this. Right here in this last sentence, it says the minerals can coat the inside of pipe and equipment, reducing flow and heat transfer. So what happens that in a small boiler, for example, a small flow-through boiler has these little heat exchangers, and we get the water flowing through. When it flows through, how come I can't change my pen color? When we have water flowing through these, you have the flames hitting these very thin, very thin heat exchangers, and as the water flows through, but inside here, as it heats up, it will coat the inside of these pipes with this hard water. And what happens is you don't get the heat transfer through that little heat exchanger, right? Because you will have a coating inside there. So these, especially these small boilers, require cleaning.
I've seen it in furnaces as well.
Okay. Well, it's just when we have water present and we heat up the water, what happens is the minerals then tend to settle out and they will coat the inside of your pipe. They will coat the inside of your boiler fittings, etc. So you need to clean these. Now, there's some products out there that will not warranty their boilers until you have a water softener, especially in Southern Alberta. Because after a year, you're not going to, whoa, what happened there? I don't even, how did that happen? I don't know. So after a year, you won't even have the same amount of heat transfer. So you won't have the same amount of heat coming to your fixtures or whatever it is that you're heating up. So sometimes they want you to have a water softener in place. Okay. So these dissolved minerals comes from the earth, of course, and a lot of water passes through chalk, limestone, etc. And then you have this dissolved in it. You have this chalk and limestone dissolved in the water. So water that passes through ironstone or iron ore may have a rusty appearance. Again, in Southern Alberta, a lot of private water supply systems have a lot of this stuff in it, and they want to treat it. They want their water to be smelling good, tasting good, so to speak. Now, does anybody live out in the country and live on well water? You may know this very intuitively. All right, so we use a couple of terms to describe hardness, and this is to designate the amount of these dissolved minerals. And there's three of them: temporary, permanent, and total. Okay. Now, total hardness, this tells us exactly how much mineral deposit, and they do it 1 milligram per liter, and that equals 1 part per million. So total hardness of water varies considerably depending upon where the water and the minerals it has dissolved. So it's classified here. And anytime you have private water supply, and that's well water is what I'm trying to get at, private water supply, you have to test it with the provincial government anytime you have a new well to make sure that it is potable. So some of this very hard water might not be, so it might be non-potable, meaning it's unfit for human consumption. All right, so that's total hardness. So there it is there. Very hard water is unfit for human consumption. Temporary hardness is considered the bicarbonates of calcium and magnesium. That's temporary hardness. It's dissolved in the water. It's because this bicarbonate settles out about 140 degrees Fahrenheit. And this is where we get those white flakes on our aerators or inside of our pipe, etc. This is what it is, all right? So they're telling us that our thermostats on our hot water tanks, you don't want to get them above 140 because you will then have a lot of this bicarbonate settling out in the form of scale if you get it too hot. Right?
Hey, sorry, Doug. Is that it kind of layers like a croissant on the bottom of the pipe, different layers and layers as it goes up, and eventually
it can, but what they're talking about here is the scale that comes out, and it's kind of white flaky stuff, right? And it sticks to surfaces after a while, and you can kind of scrape it off. Is that what?
I got a good picture. I got a really good picture.
Okay, good.
Yeah, we were just doing like a 2-inch copper line clean, or like an exchange from a hot water tank, and we cut open the line, and probably 65% of the pipe was just, like you said, layered in little white, look like crystal meth, just kind of layered all in the pipe, layer by layer by layer, and Breaking Bad kind of.
Yeah, well, I don't know what crystal meth looks like.
Breaking Bad, man, come on.
Well, I've only seen it on TV. I've never had any in my hand.
Oh, I'm just referencing TV. Come on, Doc. Come on.
Okay, all right. Okay, thanks for that, but that's true. It's 100% true. So now permanent hardness, it's the carbonates of calcium and magnesium in addition to sulfates, nitrates, chlorides, other elements, and that causes permanent hardness. You know the sludge, that black crap that comes out of boilers? This is what it is, right? For this reason, all steam boilers must be equipped with blow-offs and regularly remove sludge deposits. I underlined that and I took it out. Okay, so this is what permanent hardness is all about. Okay. Then they're getting into and start talking about oxidation, where water contains dissolved air, which is composed of nitrogen, oxygen. As you know, our atmosphere, 79% of it is nitrogen, 20% is oxygen, and 1% is other.
I got that picture in there, Doug.
What picture are we talking about?
Just calcium. I don't know if anybody wants to see it.
Oh, I didn't look. Is that in the chat?
Yeah, I just threw it in.
Okay, thank you. Now, it's making me save it.
Sorry.
That's okay. I'm trying to see it. Oh, wow. Look at that. Okay, let's
She's ugly.
share this. Okay, let me just share this for a second. There you go.
That's a beauty. That was
Hey, look
fun.
at that.
That was really fun.
Did you replace that hot tank?
Yes, I replaced the whole tank. It was leaking from where all the rust is at the bottom of it there.
Well, sure. This is also, listen, this vent looks like it's been condensing as well, causing a little bit of crap. There's all kinds of problems going on there.
Oh yeah, like the venting was leaking and stuff into it
Oh.
from the chimney. So he resealed all that when we brought the new tank in. Yeah, it was fun.
All right. Yeah, we come across a lot of stuff like that all the time as plumbers and gas fitters. That's just what we do. We fix things when we see them. So these effects of temperature on hot water heating. So this is Marty's gig on the hot water heating stuff. But again, the nitrogen is non-corrosive, but the oxygen presents in the system can cause major problems because the oxygen reacts with the metals, causing pitting, gradual weakening of the metal surface. You can get rust deposits in the piping system, especially if you're using steel. So like all chemical reaction, heat accelerates the process. All chemical actions, reactions create heat, but heat will accelerate that. So hot water lines are usually more prone to this oxidization. Now, but hot water heating systems where you use steel or iron components, that's when you get your corrosion problems. Now, most hot water systems do not present a problem, but once the air has been bled from the system during startup, the water contains very little dissolved air. But if the system is continually receiving fresh makeup water, then you get a lot of air entering, and that rate of oxidation will be rapid and excessive and expensive. Because if you look at that last picture there that Brad gave us, that is expensive, right? It starts to get expensive. So we treat our boilers and stuff like that. We use chemical compounds, etc. And there's all kinds of things that you can do. And I'm not going to explain that. So solubility. Temperature affects the solubility of these dissolved chemicals in water. Temperatures above 60 degrees C result in the settling of temporary hardness that coats the pipe walls and heat transfer surfaces. And they're talking about the boilers in here, these heat transfer surfaces, resulting in a reduction in heat transmission. So we do need to be aware of this stuff, and treatment for our systems need to happen, or else they're never going to last, right? We want these things to last. And who's going to do all this treatment work? You are. This is a part of our jobs to do this if we're asked to. Now, if you are doing any kind of boiler servicing or etc., you should know what to do. And there's a lot of literature out there on how to do that. Now, we get to density and expansion. So an increase in temperature produces a change in the density of the water, doesn't it? Because if it is warmer and those molecules are moving faster, it would be less dense, right? Remember, a cubic meter of water at 4 degrees C has a mass of 1,000 kg. So that is where water is most dense, right? Remember, water is most dense at 4 degrees C. But at 100 degrees C, the mass becomes less. Look at that. Same 1,000 kilograms of water becomes a little less because the molecular motion is increased. Okay, no big deal. We know this, but that's where things kind of go awry because you get different pressure changes, etc. Now we're going to talk about buoyancy. So I have this little video I want to show, and this is on Archimedes' principle.
Some of the best opportunities to learn are the moments in which we are perplexed, those moments in which you begin to wonder and question. These moments have happened throughout history and have led to some truly amazing discoveries. Take this story, for example. There once was a fellow named Archimedes. He was born in 287 BC in the city of Syracuse in Sicily. He was a Greek mathematician, physicist, engineer, inventor, and astronomer. One day, Archimedes was summoned by the king of Sicily to investigate if he had been cheated by a goldsmith. The king said he had given a goldsmith the exact amount of gold needed to make a crown. However, when the crown was ready, the king suspected that the goldsmith cheated and slipped some silver into the crown, keeping some of the gold for himself. The king asked Archimedes to solve the problem, but there was a catch. He couldn't do any damage to the crown. One day, while taking his bath, Archimedes noticed that the water level in the bathtub rose and overflowed as he immersed himself into the tub. He suddenly realized that how much water was displaced depended on how much of his body was immersed. This discovery excited him so much that he jumped out of the tub and ran through the streets naked, shouting, "Eureka!" which comes from the ancient Greek meaning, "I found it!" What did he find? Well, he found a way to solve the king's problem. You see, Archimedes needed to check the crown's density to see if it was the same as the density of pure gold. Density is a measure of an object's mass divided by its volume. Pure gold is very dense, while silver is less dense. So if there was silver in the crown, it would be less dense than if it were made of pure gold. But no matter what it was made of, the crown would be the same shape, which means the same volume. So if Archimedes could measure the mass of the crown first and then measure its volume, he could find out how dense it was. But it is not easy to measure a crown's volume. It has an irregular shape that's different from a simple box or ball. You can't measure its sides and multiply like you might for other shapes. The solution, Archimedes realized, was to give the crown a bath. By placing it in water and seeing how much water was displaced, he could measure the volume. Then he'd calculate the density of the crown. If the crown was less dense than pure gold, then the goldsmith most definitely cheated the king. When Archimedes went back to the king and did his test, the story says, he found that the goldsmith had indeed cheated the king and slipped some silver in. These days, using the way an object displaces water to measure volume is called Archimedes' principle. The next time you take a bath, you can see Archimedes' principle in action. And maybe you'll have a genius idea of your own.
Okay, so that was Archimedes' principle. where he used the principle of water displacement to figure out volume of an object. Okay, so what I'm going to talk about in this is we're going to use Archimedes' principle to solve for a bunch of different things. But what we're going to also do is talk about the 3 laws of buoyancy. Now, in the plumbing, first off, buoyancy is demonstrated by any float operated device, like a float ball that operates a ball cock in a water closet. It's just a simple thing as the water level rises, and you could have different kinds of ball cocks, but as the water level rises, so does the float in there, and it just rises and shuts off the water. That's really, it operates a switch. That's all it does. And it uses buoyancy to do that. So they tell us in order to troubleshoot and service some of these devices, we need to understand buoyancy. Okay, buoyancy is the force acting on any object immersed in a liquid. Now, a liquid can also be air, by the way. Okay, so any object immersed in a liquid appears to lose mass due to the upward force exerted by the liquid. And if it's in air, it's gravity. But what this upward force that we're talking about when it's in water is called buoyant force. This is buoyant force, this upward force, okay? It makes things weigh less when it's immersed in a fluid. And the fluid that we are going to be mostly using is water, fresh water. Okay, so this is what we're going to talk about and how we calculate these buoyant effects. Next, we need to talk about the 3 laws of buoyancy. Now, there is a little thing here in italics that we should understand first. A body immersed in a fluid loses as much weight as the weight of the fluid it displaces. So we're going to do some calculations around this, and we're going to figure that out. Now, the weight of the fluid displaces will also be directly related to the volume. And we'll figure that out in a second. So here's the 3 laws. 1, a body sinks in a fluid if the mass of the fluid displaced is less than the mass of the body. Okay. So number 2, if a body displaces a mass of fluid greater than its own mass, it will float. We'll talk about that too. A body remains in equilibrium, neither rising nor sinking, if the mass of the fluid it displaces equals its own mass. Then we have a little bit of a demonstration here. So in this figure 5, they have this 1 cubic foot box, okay, or block, and it's lowered into a tank. And as that goes into the tank, the amount of fluid it will displace is equal to the volume of that block. Now, because we're using water, we can calculate the buoyant force exerted on that block. Because water, we know 1 cubic foot of water weighs 62.4 pounds per cubic foot. Yes? So this water right here, this cubic foot of water weighs 62.4 pounds because it's a cubic foot. So the buoyant force pushing up on this block will be 62.4 pounds. Now, we haven't really said how much this block weighs. So for example, if this block weighs 100 pounds and I immerse it in this water, while it's in the water, if we take 100 and minus off the buoyant force that's on there, this block, while it's immersed in the water, weighs 37.6 pounds. That's all this weighs. This block right here only weighs 37.6 pounds when it's immersed in fresh water because of its volume. This is the only way I could sweep my girlfriend off her feet, is when we're in the swimming pool, because there's buoyant force being pushed up and I can then carry that person. Yeah, does that make sense? A little bit? Okay, we're going to go through this a little bit more here. So now the next picture shows you how that is. And there is that block, 31.2. Okay, there's this block and it weighs 100 pounds. And then when it is submerged in that fresh water, that block will only weigh 37.6 pounds. That's right, Brad. You don't want to lift weights underwater. It's not the same. So this is what we call buoyant force. So the buoyant force pushing up on that is directly related to its volume. So buoyant force is directly related to the volume of the object, right? It will tell us how much that is. Now, this particular next picture on here in figure 7 shows that this block only weighs 31.2 pounds. But it is 1 cubic foot, right? So the buoyant force going to be pushing up on this object is going to be 62.4 pounds because of its volume. But because this only weighs 31.2 pounds, we have a buoyant force of 62.4 pounds. This thing will float, and it will actually float almost half of it will be above the water because, as you can see, how much buoyant force is pushing up on that object. So if a body displaces a massive fluid greater than its own mass, it will float. It will displace because of its volume. If I completely submerge this underwater, this will have 62.4 pounds of water displaced on it. So the next picture, in a slightly different situation, if this 1 cubic foot box weighed 62.4 pounds and we put it in the water, listen, it's going to weigh nothing when it's in the water, but it's not going to sink and it's not going to float because these are equal in here. So this body remains in equilibrium, neither rising nor sinking. If the mass of the fluid it displaces equals its own mass. So let's remember now that buoyant force is equal to the weight of the displaced liquid. Maybe, Brad, maybe. The weight of the liquid displaced equals the volume times the density of the liquid. And then they give you some examples, but you can look at those examples yourself. I will give you different examples. So let's have a look at some of these examples. So if I had a block, because I want to ask you a bunch of different questions on these things. If I had a block of material and it weighs, so its mass is equal to 900 pounds. Okay, and it has a volume of 5 cubic feet. I'm going to ask you a bunch of questions on this. First off, what is its density? Remember, density is mass per unit of volume. So density is calculated by taking the mass divided by the volume is equal to its density. So we will take 900 pounds divided by 5 cubic feet. And this comes out to a density of 180 pounds per cubic foot. It becomes very important that you get your increments of measure correct, right? And always label them on your numbers. Now, the next question I'm going to ask you is, what is the relative density of this object? Now, the relative density is how many more times heavier it is than water, right? So I'm going to give you another formula triangle here. If I can get a triangle to work, here we go. We take the density of the object and we divide it by the density of water or air, if it's a gas, but if it's a solid or a liquid, it's by water. And that will give us our relative density. So 180 pounds per cubic foot is the density of my object. I will divide it by the density of water, which is 62.4 pounds per cubic foot. And the relative density of this object is 2.88 times heavier than water. The next question I want to ask you about this is, what is its buoyant force? So that's buoyant force. And the buoyant force is calculated by taking the density, the density of water and multiplying it by the volume of the object. So the density of water is 62.4 pounds. The volume of the object is 5 cubic feet up there from the top, right there. And now the buoyant force pushing up on this object is 312 pounds. And the next question I could ask you is, how much does it weigh in water, this object? So I know this object from before weighs 900 pounds, and I minus off the buoyant force off it. So this object immersed in water weighs 588 pounds. And this is one of the reasons why they used waterways to transport logs, because they are weightless almost when they are in or submerged in water, and they can move them quite easily. Let's do another couple of examples of this. Next question. An object weighs let me just see here. An object weighs 300 kilograms. Okay, so there's the mass. And it has a volume of 0.7 cubic meters. I want to know the density. I want to know the relative density. I want to know the buoyant force. So I want to know these three things. As you know, density is calculated by taking the mass divided by the volume is equal to the density. So the density is 300 kilograms divided by 0.7 cubic meters. The density of this object is 428.57 kilograms per cubic meter. Now, the relative density, I take my density of my object, 428.57 kilograms per cubic meter, and I divide that by the density of water, which was 1,000 kilograms per cubic meter. And the relative density of this object is 0.42857. The buoyant force is calculated by taking the density of water and multiplying it by the volume of the object. So that's 1,000 kilograms per cubic meter multiplied by 0.7 is the volume of this object. And that is 700 kilograms is the buoyant force. So the last question is, how much does this object weigh when it's submersed in water? Just shout it out.
Can you put that back up there for a sec, please?
Yeah.
400.
How much does this object weigh?
400 kilos.
It weighs nothing because the object only weighs 300 kilograms. And when it's submerged in water, it has a buoyant force of 700 kilograms. So we have a negative number. So this object weighs nothing when it's in the water.
On our buoyancy triangles in the book that you made for us,
Yes.
the triangles themselves are almost kind of confusing to follow.
So listen, I'm going to give you 3 triangles right now. Actually, I'll give you 4. Okay, you ready? Okay, here we are. So we have this first one, and this is density, right? Where mass, volume, density. So this is the density one. Second, I'll give you relative density, where we take the density of the object divided by the density of water or air, and that will give you your relative density. The next one I'll give to you is for buoyant force. So the buoyant force is equal to the density of the fluid that it's in, water or otherwise, and multiplied by the volume of the object. And then one more. If I take the mass of the object and if I divided it by the buoyant force, that will also give me my relative density. So you could use those 4 to do any of these calculations.
The last three, they're all density. They're all defined density.
Yeah, well, it's the density of the fluid. So if I'm talking about density of fluid here, I'm talking 62.4 pounds per cubic foot. We're talking about fresh water, 1,000 kilograms per cubic meter, right? That's what I'm talking about. Density of water. Those are two densities of water, density of the fluid. Does that make sense? This is density of the object. This is buoyant force. This is mass of object. In air. This is the mass of the object in air or in front of us in the atmosphere. Okay. Let's do a couple of more questions. Yes? Why not? Okay. Next question. I have an object that weighs 1,700 kilograms. Okay, mass. I have this volume of this object is equal to 9 cubic meters. What is the density equal? Well, we know density triangle is take your mass and divide it by the volume. So the density of this object is 188.88 kilograms per cubic meter. The relative density of this object is right up here. Take the density of the object, 188.88 kilograms per cubic meter, and divide that by the density of water. And now the relative density of this is 0.1888 times heavier than water. The buoyant force of this object is take the mass of the object in air. Oh no, I got that wrong, didn't I? It's the volume. Did I get that wrong? No, here is this. Volume of the object, 9 cubic meters. Multiply that, right here, multiply that by the density of the fluid, 1,000 kilograms per cubic meter. The buoyant force is 9,000 kilograms on this object. Now, how much mass would it take for me to submerge this object underwater? Like how much force do I have to push down on this object to get it to sink? Anybody know? Well, first off, I have 9,000 kilograms of buoyant force. The object weighs 1,700 kilograms itself. So that brings me up to 7,300 kilograms. I would have to take this object, if this is what I have to push down 7,300 kilograms on top of it to get it to go under water.
Hey, Doug, what was the 1,700 kilograms again from?
That was the mass of the object right here.
Right. Sorry. Thank you.
Right at the beginning.
Gotcha.
Yeah. Okay. Awesome. So we do a couple more. I think yes. Let's do a couple more examples here. Okay, so let's get something a little more. Okay, so I have an object that weighs, ooh, what am I doing here? Weighs, I gotta stop pressing buttons. That weighs 340 kilograms in air. Okay, so that's just what it weighs lying on the ground here. So, but if I put it in water, if I put this object in water, I'm going to tell you that it weighs, when it's in water, 137 kilograms. Okay. So now I want to know the buoyant force. I want to know the volume of that object. And I want to know the density of that object, and I want to know the relative density of that object. Now, when we have an object, what it weighs in air and what it weighs in water, we can calculate the buoyant force simply by taking 340 kg minus 137 kg, and that is going to equal my buoyant force, minus 137. So the buoyant force is equal to 203 kilograms, is the buoyant force on this object. Now, the volume, I could calculate the volume because the volume is directly, so let me just write this. The volume is directly related to the buoyant force. So I could take the buoyant force, which is 203 kilograms, and if I divide that by the density of the fluid, that gives me the volume of the object, and that is going to equal 0.203 cubic meters is the volume of the object. Now, this is equal to buoyant force, 203. Now that I have the volume and I have the mass of what it weighs in air, I can get the density. The density would be 340 kilograms. That's what its mass is, divided by the volume. Gives me my density, and that comes out to 1674. And there's the density of that object. And now I can get the relative density because I have what this is. So that's 167.8, oh, 74.87 kilograms per cubic meter divided by 1,000 kilograms per cubic meter. The relative density of this object is 1.67487 times heavier than water. Now, the quick and easy way to get the relative density of that, I told you that there is a little bit of a formula triangle to do that. So we take the mass of the object and divide it by the buoyant force is equal to the relative density. So let's do that just to prove that point. So the mass of the object was 340 kilograms, And if I divide it by the buoyant force, which is 203 kilograms, and that comes out to 1.6748. 7. So that's a quick and easy way to do a relative density of that object. I'll give you a minute to catch up there. Okay, let's get back to the whiteboard. Okay, so here we are. I'm going to give you some more. Here we go. And I'll work it out with you on this one, and then I'll give you one to do on your own. So this one, I'm going to say an object weighs 757 pounds in air, or as it sits on the floor. And I'm going to say when the object is in water, when I submerge this object in water, it weighs 728 pounds. Okay. So now I want to know the buoyant force. I want to know the volume. I want to know the density, and I want to know the relative density. So to do this, the buoyant force, if I have these two numbers, 757 pounds minus 728 pounds would be equal to my buoyant force. And that is 29 pounds. So my buoyant force is 29 pounds. Now, the volume is directly related to the buoyant force. So I have 29 pounds of buoyant force. I divide by the density of the fluid that it's immersed in, and that gives me my volume, because you can see the pounds get crossed out on this. So my volume of this object is 0.4647 cubic feet. Now that I have the volume, I can get the density by taking the mass of the object and dividing it by the volume. And that would give you my density, and that equals 1629.008 cubic pounds per cubic foot, excuse me. Pounds per cubic foot. And now I can get my relative density by taking my density, 1629.008 pounds per cubic foot, and divide it by 62.4 pounds per cubic foot. And my density or relative density comes out to 26.1059 times heavier than water. And now I will give you another question to work on. And let me just stop recording for a second.